Welcome to another video, and in this video we'll be demonstrating the deployment of NRDC, which is the dual connectivity for next generation 5G capabilities. So this documentation is basically by free5GC, in which they demonstrated what is NRDC, how it actually works, and after that we'll be using this free-RAN UE, which is a simulator by free5GC in order to test the new radio dual connectivity feature in free5GC. So we'll come to this documentation later. Before that, this is the beginner-friendly documentation introducing the NRDC concept. So if you go a bit down, you can see what NRDC exactly is. It's a new radio dual connectivity. It allows the UE to be connected to two different NR cells simultaneously. So what it means is basically your UE will be connected to two G node Bs at the same time, and the first G node, the main G node B is called as master G node B, and the secondary G node B is like as a backup. And then we have the core network. So both the G node Bs are connected to the same core network. So the architecture basically consists of two main aspects. The first one is the network interface, and the second one is the radio protocol stack. So if we talk about the network interface in control plane architecture, it's pretty simple. We have the main G node B and the secondary G node B, and the main G node B is connected to AMF in order to transmit the control plane packets over the NG interface. And then the main G node B and the secondary G node B, they both are connected over the XN interface. And if we talk about the radio protocol stack, so similarly we have the master G node B and the secondary G node B, and they are connected over XN, and now both of these are connected to the UE over the RRC in order to maintain the RRC state of the UE, for example RRC idle to inactive to connected state, and ensuring the control of the connection. So both of the master and the second G node B maintain their own RRC protocol entities to the RRC UE. Then we talk about the user plane. So in user plane, the master and the secondary G node B both are connected to the UPF in order to share the user plane data. And here we have some good concept for the radio protocol stack. You can see in the user plane protocol architecture, the NRDC implement three different designs. So these three different designs are basically, the first one is the MCG bearer, and then second one is SCG bearer, and then we have split bearer. So in MCG bearer, the control plane messages and the user plane data both are served by the master cell or the master G node B. Whereas in this, the control plane messages are served by the master G node B, but the user plane data is served only by the secondary G node B. And in the split bearer, as the name suggests, it's basically the control plane message is served by the master G node B, and the user plane is served by both the master and the secondary G node B. So now here is a little bit more detail about the PDU session split and everything, why it is important and how NRDC work. So if we have a look on to how NRDC work, it's basically about the PDU session establishment. So UE basically initiate the PDU session establishment request, and AMF and SMF coordinate it to set up the session as usual, and then UPF allocate two set of TEIDs. So this is the main point here for dual connectivity. So the one TEID will be for the master G node B path, and another TEID will be for the secondary G node B path, and we'll be having that on the terminal as well in the overall networking, how these things are set up, and we'll have a look on the logs of the basically the PCAP logs, in which we can see the different TEIDs and source and destination for both master and secondary G node B respective to the UE. And then we have some bearer configuration, which basically which aspect or which type of bearer will be used, and then some dynamic flow management, and then inter-G node B connection over the XN interface. So yeah, it's a brief documentation on how this NRDC work and what actually it is. So you can have a look on it to have more details. So if I conclude everything, it's more like, so it's more like that you have a single 5G core network in which there are two G node Bs connected to it, and both of them are connected to the core network, mainly to AMF and to UPF, in order to exchange the control plane and the user plane messages over the NGU and NGC tunnel, like the N2 and N3 interface. And then this master G node B and the secondary G node B, both of these are connected via the XN interface in order to share the data of the control and user plane. And then both of these are used to maintain the RRC state of the UE and connected to the UE via the via the UU interface. So now let's move to the free-RAN UE. So this is a new, I would say, simulator kind of, for 5G RAN and UE, which is developed by free5GC and by this guy. And so the primary goal of this simulator or this project is to create a simulator for testing the NRDC concept in free5GC. And the key innovation of free RAN UE is basically the implementation of user space GTPU. So it basically replaced the GTP 5G module, which was traditionally in the kernel space. And so this approach is basically provides flexibility over the GTP packet manipulation, and it makes easier to customize and manage the packets. So today we'll be testing the NRDC concept. For that, we can go to user guide, and here if we go a little bit down, you can see in the advanced features we can see these different documentation on testing the static, dynamic NRDC, and there is something called as multiple UE, which we'll maybe have a look later. So if we go to the static NRDC, so firstly we'll try to replicate this documentation or this deployment into our VM, and we'll try to see if we can establish the connection of the UE with the both of the G node B, which are connected to the same 5G core. So it basically, there is a caution that says that the master G node B and the secondary G node B, you should not run both of them on the same machine because of the GTP port conflict, because they will be running on the same GTP port. So on the same machine, it will create some conflicts. And also for the UE, you should also not use the same machine as free5GC because of the data plane forwarding issues. So for that, we have two options. The first one is to use separate machines. If you have access to multiple VMs, you can use that. And the second one, if you are limited with the resources and VMs, what you can do is you can use this namespace separation documentation, which I will be using in order to do everything on the same virtual machine using different namespaces. So we'll be creating multiple namespaces for each of them. For example, we'll be creating a namespace for UE, one namespace for the 5G core, and two namespaces for the master G node B and the secondary G node B. And if you want to deploy on different machines, so you can follow this guide, and it's pretty simple. So you should not face any issue. Then okay, so let's go to the namespace documentation for the static NRDC deployment. So okay. Starting with the architecture overview, as we already mentioned that the GTP port will create an issue, we'll be using the namespaces, basically 4 namespaces for each of these, the core, master G node B, secondary G node B, and the UE. And so it will basically reduce the requirement of bringing up the real machines or 4 VMs. So if I can zoom in a little bit here. So this is the overall diagram, I would say, or the architecture topology that we'll be using the namespaces. So the first thing here is the 5G core, which is by free5GC, and we'll be replacing the AMF and the UPF IP with the following IPs. And because initially we'll be creating the host bridge on to the 1001X, and then the AMF will be connected to the master and the secondary G node B for the control plane message exchange via NGAP. So you can see now on the master G node B, we have two bridges. The first one is in order to connect with the 5G core on the same subnet, which is 1001X, and the second one is on in order to connect with the UE, which is on 1002X. So you can see in the subnet 1001X, you can connect to AMF, and also in the secondary G node B, it's 1001X. It's able to connect to the AMF as well. And similarly for the user plane packet, so the data plane package will be connected to the UPF in both of the G node Bs over the same subnet interface. And for the UE, we have different subnet interface, which we'll be using to connect to the UE in order to exchange the control and data plane packets to the UE. So, and both of these are connected via the XN interface, both the master and the secondary G node Bs. Okay, so now we can move on to the prerequisites and everything, and let's start with the terminal part in order to practically see the things, how we can deploy and test everything end to end. So for that, let me shift to the terminal part. Okay, so now this is my terminal setup. Basically it's just a VM, single VM on which I have already deployed free5GC, because the deployment of free5GC will take some time, so I just skipped that part. And if you want to do that, they made it very simple. I can show you the documentation that I followed. You simply will go to the user guide, and in the user guide you will go down to the quick setup on the single host mode, and here you can see this is the ultimate one script setup. and I really liked it because you need not to do anything. It will install all the things, all the requirements, MongoDB and everything with just this simple script. So just before proceeding, just make sure that you follow the following requirements or prerequisites, and after that you simply need to clone the free5GC and find your interface on which the machine is connected to the internet, and simply run the script. That's pretty much it. You need not to do anything else apart from this, and it will set up all the components of free5GC and will do everything for you. So in my case, I've already done that, so I can skip this part and we can move towards the terminal. So the first thing that you will do after compilation and everything is basically to configure the free5GC according to the namespaces. So with these prerequisites are already done by that script. It installed Golang, GTP5G module and MongoDB. So you will simply run the script and it will do all the things for you. And after that, we can skip these things and we can come to the namespace setup, which is the main part from where we will start today. So the first thing you will do is to basically clone the free ren UE repository. In my case, I have the repository here. So after that, you will just do make, and after that you will bring up the namespaces. So there is a small typo. It should be make dc ns up, so you should be using p by yourself. And if you do tab, you can see either you can use this or this, but both of these are different. So in order to set up the namespace, you will be using the up command, and that's it. After running make dc namespace up, it will basically set up the namespace on your machine, and that's it. I don't think you need to do anything else apart from this. You can see the free mran namespace, free sran namespace, and for the UE as well. And you can see the network topology that we already saw in the diagram. And we can also do IPA, and you can see here, this is my main interface which is connected to internet, and now it created a bridge for the host, which is 10.0.1, and then we have bridge for the master RAN and bridge for the SRS RAN. Okay, so now the next step is to configure your free5GC. So your free5GC for now is pre-configured with some IPs, default IPs for the NGAP, for example N2, N3 and N6. So you need to configure the NGAP or N2 and then N3 and N6 IPs according to the namespace that you created, in order to make sure that the free5GC will run in the same namespace, in order to match all the routing between the G0Bs, the core and the UE. So for that, let's move back to this terminal, and you can simply modify the network configuration. They provided the description and everything. Simply, in my case, I've already done that, but I can show you the exact location or the changes that I did. So this is the amfconfig.yaml, and in this what you need to do is you need to replace the ngap list IP from this to this. So we'll search for the ngap list IP list, and I've already changed the IP to this. In my case it was by default this, but it could be anything, so you simply need to replace it with this IP. Similarly for the smfconfig YAML, you will be doing the same thing. So in this YAML, what you need to look for is basically the N3 interface. So let's see where we can find it. Okay. Oops. This is the amfconfig. I can search for the entry like this. Yeah. So you can see the endpoint for the N3 interface. Here you need to change the IP again. And the last one is for the upf.yaml. This time I cleared the terminal so that I do not mess up with all the configs. And you can find here the what you need, GTPU, GTP5G interface. Yeah, this one, GTPU, and this address we need to change. So after that, your 5G core is configured. And these are the only three things that you need to do in the 3 config files. And after that, you need to make sure that the IP forward is enabled. So let me do that as well. And here you will be using the interface which is connected to internet. For example, in my case, it's ENS3. And then we'll be using these 2 commands: disable the firewall and enable the perfect. Now we'll be running the 5G core. Okay, now it's trying to connect to the web console, which we have not initialized yet. So let's move back to the another terminal and let's start the web console as well. Okay, now we can see web console is working fine, and the core is also connected to the web console now. So now let's create a new tab and let's open the so let me quickly log in. For login details, you can find the details here and go to this documentation. We have already done this, so no need to do this. You can simply access it on the 5000 port, and the credentials are this: admin and free5GC and login. In my case, there is 1 subscriber. I can delete it and create a new one again with the default configuration. You can see you can change the IMSI or the PLM and ID tag values, key OPC, everything, and you can also modify the QoS parameters according to your need. In my case, I will proceed with the default configuration, and you can see the subscriber is now created, and you can also see it in the logs. It fetched basically the APIs to get the subscriber deleted and then to add one. So now we are ready to move to the next step. Also, you need to make sure there is a flow rule 111132 under the network slice, which we can check. Yeah, you can see under the flow rules we have the IP filter for 1111/32. So make sure that in your case it's like this. And after that, let's start the G0Bs. So we need not to configure the G0B files, they are already pre-configured. So let's enter the namespaces that we created. For that, I have another terminal. Let me create some space in order to see the different logs when we attach the G0B and the UE. So here I have the same VM, and let's go inside the namespaces. For example, here I'm going inside the DC namespace for MRAN, and now we can just start the G0B. But before that, I would like to show you the config file or the YAML file that we are using. So this is the config file that we are using for the master G0B, and you can see in this file we have very minimal configuration. For example, it's up to the point. We have the AMF N2 IP and the UPF N3 IP, and what we can do is we can go a little bit up and compare it to this diagram. It will be more convenient to understand all the things. Okay, let me set it over here again, and yeah, perfect. So here you will see we have the AMF N2 IP, which is the same one we set in the config files with the same port, and then we have the UPF IP, which is the same IP but we have different ports. For example, you can see the port number defined here, and then we have the RAN N2 and N3 IP in order to connect to the control plane and to the data plane. So this is the 10012, the same IP, and for the N2 we have 10012. Yeah, perfect. It's N2, and then we have N3 10012. Yeah, and then we have the port number defined over here for the N2 and N3, 38412 and 2152. So here we have for the control plane 38412, and for the data plane we have 2152. And similarly for 10021 interface, which we are using here, 10021, in order to connect to the UE. So this is a different subnet, and this is on a different subnet. And then we have the ports defined over here, and then port for the RAN control plane IP and RAN data plane IP. And then we have RAN ID and the name of the G node B, PLMN and tag information, and the network slice information as well. And now this is the important part, because here we are defining setting the XN interface to true, and we are also setting the IP of the XN interface. For example, the listener of the XN interface is this main G node B, which is the IP, which has the IP 10012, and then the secondary G node B will be having the IP of 10013. You can see here. So yeah, and then we have the port definer on which there will be the XN interface, and that's pretty much it. Also, we can see the same things in the secondary G node B. So let's go inside the namespace, and again let's have a look onto the config file. Perfect. So you can see we have similar things. We have the IP for the N2 and N3 interface, and for the RAN N2 and N3 interface we have 1.3. In the last case we had it for the main G node B, we had it like 10012, but here we will be using it 10013 in order to separate the things. You can see the same thing is demonstrated in this diagram or the topology. And then we have the RAN control plane IP and the data plane IP in order to connect to the UE, which is this IP, which is connected to the UE. And then we have the ports, and the name is secondary G node B, same PLMN tag and the network slice information. And again we have the XN interface details. And after that we can go inside the UE as well, and let's see the config file for UE. In the UE you can see we have the RAN control plane IP, data plane IP, and the local IP as well. And the PLMN information, authentication parameters, integrity algorithm, all these things, PD session, for example the DNN and the network slice information for the PD session. And then for the NRDC we set it to true, and you can see the data plane IP and the port number as well, 10031. Okay, and now let's start the G node Bs. For example, let's start the master G node B initially. So the master G node B started, and you can also see the logs in the AMF. We can see the ng setup request and response, and in the master G node B logs we can see it is connecting to AMF with the following IP, same as stated in the diagram, on the same port, and it's trying to set up the N2 interface. Then with the G node B information, the same thing we saw in the config file, and you can see the N2 setup is complete. And also now it's trying to connect to the UPF for the data plane, and on the same IP. And now it's also started the XN listener on this IP in order to connect to the secondary G node B as well. Now you can see the RAN control plane listener started on this, and data plane on this, and GTP started and everything. Perfect. So the G node B, or I should say the master G node B is started. Now let's start the secondary G node B as well. Perfect. And we can also see the logs for the secondary G node B, and we set up request and response, and also similar kind of logs connecting to AMF on this IP, G node B information, and to setup complete, and connecting to UPF and XN access address, and same kind of RAN data plane and control plane addresses. And you can also see the G node B is also started here. Nice. Now we can move to the UE part. So we are already inside the UE namespace, so we can start the UE directly. Okay, we can enter some spaces, and here as well. Perfect. Okay, so now the UE is connected, and we can see the logs in the G node B, the master G node B. So you can see the new UE connection is accepted from this address, and now it's trying to set up the N1, and The UE with following MC is initialized, PDU session establishment, request and response, and it's completed. And now it's waiting for the release, which we are not going to do soon. So yeah, and it also allocated the IP to the UE, which is 10.022. Perfect. And also here you can see the XN connection accepted from this. So now G0B, both of the G0Bs are connected via the XN interface, and also it's connected to UE, and the data plane address for the UE is 10.032. In order to see the things more clearly, we can go inside the UE and I can do IPA, and you can see we have the IPs for both of the G0Bs allocated over here in order to access the data plane packets. For example, here we have this for the master G0B, and for the secondary G0B we have this, which is the same one, so you can see in the logs. And then this is the main UE tunnel IP over which we'll be testing the internet. So now everything is fine, and you can also see the logs of the UE. Started the UE with the following MC, and it's connected to the RAN control plane, and the PDU session IP is this. And you can also see the PDU session QoS rule, which is we already saw in the web console, and the DNN and network slice information and everything. And also it's connected to the RAN data plane to this IP. So, and the tunnel is also up, and you can also relate the things in the diagram if you can remember the same IPs 10.022, 10.021 and everything, how they are connected and what is going on. You can just simply pause and have a look on to grasp the things. And after that, let's move to the next step, which is obviously an ICMP test in order to test the things if everything is working fine or not, and in order to basically see if we can exactly use both the G0Bs with one UE. For example, we'll perform a ping test with -I using the tunnel of the UE namespace, and we'll be pinging 8888. Perfect. So before that, I would like to start PCAPs on the following master and secondary G0B. For that, I will go inside each of them. For example, for the master G0B and for secondary G0B. Now I need PCAP for both of them before running the ping test. So I will be using the PCAP command. Here we are basically going inside, which I don't think we need it anymore. Perfect. So we are just using TCP dump on the interface of the master G0B, and we're using the port 2152. That's it. We are saving the logs in this file. And similarly for the secondary G0B, we are using this interface, and all the parameters are the same. Perfect. So I just started the okay, my bad. Yeah. So you can see the logs. It got 0 packets for now, and as soon as we'll do the ping test, you can see it got the packets. This is the master G0B, and it got 10 packets for 5 ping request. And also if we do ping via the secondary G0B using the flow rule that we added in the web console, so for now you can see we got 10 packets here using the last ping command, and we got 0 packets here. And if I run the command again using 1111, you can see now it started getting the packets. Perfect. So I think it's working fine. Now let's quickly have a look on the PCAPs. Let me open it into the Wireshark. Okay, so here I have the PCAPs for the master and the secondary G0B. Somehow they look similar, but if we go inside and see if we can find the actual difference. So the first one is the GTP packet, and if we go inside it, we can also open it on the same on both the sides, and I can just reduce it to maybe this size because we don't want this. And from here we can see the packet difference. For example, if we go a little bit down inside the internet protocol version, So here you can see we have the source address on both the pcaps is different, and this is the source address of the master G node B, whereas this is the source address of the secondary G node B. If we see here in the diagram as well, so 10.0.1.2 is for the master G node B and 10.0.1.3 is for the secondary G node B, and the destination is basically the same, 10.0.1.1, which is the core network. And if we go a little bit down as well in the UDP, we can in a GPRS tunnel, we can actually see the TEID as well, which is different in both of these. Here we have the 2 and here we have it as 3, and the message type in both of these is TPDU. And if we go a little bit down, here you can see we have the source address, which is the IP of the UE, and the destination address, which we basically use to ping to do a ping test. For example, when we did a ping test to 8888, it was basically for the master G node B, and when we did it to 1111, it was basically for the secondary G node B. And both of G node Bs were working at the same time, and you can also see it in the logs and the PCAPs. So yeah, that's pretty much about the NRDC deployment in the static mode, and maybe in the later videos we can have a look in the dynamic mode as well. So till then, thank you so much and see you in the next one.